is barking. She's very excited.
About astronomy? Who wouldn't be? Yay!
Yay!
Hey, astronomy, hey. Hey all, those of you watching, once again, you gotta tell me that you can actually see me. This is really important because sometimes we click the start broadcast button and nobody can see us. Then we think we're doing a show, but we're really not doing a show. We're just like talking to each other, which we do sometimes. But yeah, you gotta say, hi, we can see you.
Yeah, we managed to actually, on Learning Space, have a show embedded in a show with, like, it was chaos. So, yes. You are live, is what Nancy Rosianna
I saw it.
Okay.
I saw it. It happened. So now I'm about to say hi to everybody, to the 11 of you who showed up at this weird time. Thank you. But don't worry, it's for a good cause. Pamela's going to go to Prague.
I'm flying through Prague, driving a couple of hours out of Prague to the city of Olomouc for the Academic Film Festival of Olomouc. And yeah, I'm going to go give talks that accompany science documentary films and talk about fossil hunting on Mars.
Is there something that I'm not aware of about the number of fossils on Mars?
We haven't found them yet, but I'm going to talk about how we would find them.
Right. Okay. Okay, I'm going to say hi to just a couple of people today because obviously this is a ridiculous time. Hour. Yeah. Charles Messenger, David Trogue, Fleming Thunberg, Gazelle Sabarin, Greg Nickel, Michael Collins, the astronaut, maybe, Mike Dennison, Nancy Graziano, and Steve Heistand. The guy who orbited the moon but didn't actually get a chance to land.
That would be super cool, but there's a lot of people with the same names, so I'm just going to stare mysteriously at our YouTube comments.
At our YouTube comments? Okay.
Because the link you gave me to our comments is on YouTube.
I understand now. It's hard to both like put data out in that do a show and also absorb the data that comes in. So yeah, it's multitasking that the human brain is actually incapable to do, right? So
we can hold up to 7 slots of information, and I, at this point on a Friday, can hold 3.
Yeah, and how many of those are jingles from commercials that played when you were a kid? Paul Stewart says, finally, a time that works for upside down peoples. Paul Stewart, the upside down astronomer. Nancy Christmas says, it's tough doing 2 shows in 4 hours. No, it's fine.
It's actually easier when they're back to back, which seems weird. But this whole, like, I got to go do other things somehow makes it weirder.
If I could, I would record 50 episodes of Astronomy Cast in 2.5 days, and then be done for the year. But I don't.
Okay, we can do that. We'll call it the Astronomy Cast Hangout-a-thon.
Right. And then we'll just record the entire year's worth of shows. But I don't think people would like that.
No.
Bill K, Johnny Zed, Peter Liverdink. Yay, more Australian positive scheduling. Oh, we live on a sphere, don't we? Oh, man.
We do.
Yeah, it's rough. Yeah, this is awesome. We got all the Down Under folks. So this show is just for you.
Happy Australians. We love you.
Yeah, we do. Yeah, maybe we should do that. Would that be too weird?
Go to Australia and record 50 episodes all at once? We need to do that.
That would be a little too weird. But I'm more thinking about, like, every now and then we do a special show just for the Australians.
I think we need to do that because we love Australia and they love us
that would be fun.
Can we do it in Australia? Can we do it in Australia? Can we please do it in Australia?
Hey, if Australia wants to bring us there, you were there just a couple of years ago. So.
I was.
Yeah. I have never been there. I will someday. Okay. Well, it's 5:05. I think it's time for us to make a thing that we'd like to call Astronomy Cast.
Okay, we can do that. I am. That's the wrong device. Hold on. Something is not right. There we go. Okay. I am ready to press record. Are you ready to press record?
I am ready to press record.
I am pressing record. I have pressed record and it is recording.
I am also recording. Hello, Preston.
Hello, Preston.
All right. Let what must be done be done. Astronomy Cast, episode 411, The Science of Sunset Colors. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good, and you're going to be traveling for a bit.
I am. So we're recording this on a special weird day because I'm about to go and spend about 12 days in the Czech Republic, which is not part of the EU. So there is no State Department warning on traveling there. And I'm going to be attending the AFO Academic Film Festival of Olomouc, which is run by a group of really wonderful young people. And the festival is 51 years old, which means the festival has been going on showing documentary science films since before we landed men on the moon, which is just all levels of awesome. I love doing this. It's a real privilege to get to go and be a guest.
This is one of the ones that you always look forward to every year, and I know this is great. So cool. Well, have a good, safe trip, and we'll see you when you get back.
Yes.
So we all enjoy beautiful, multicolored sunsets. But what causes the brilliant oranges, pinks, and purples that we see, and why does it change from day to day and season to season? Okay. You threw this one into the docket.
I did.
And are you getting good sunsets right now? This is actually sunset season here on the West Coast. In like March, April, and into May a bit, we get the gray clouds that just hang over our area. They dissipate and we get these really great big kind of fluffy clouds, stuff that sort of changes the view of the sunsets and the sunrises every day. And it's a really great time to see the skies. And then come summer, then it's pretty much clear skies and we don't get a lot of great sunsets. So what's going on?
Well, so personally, right now we still have daylight, and judging by the absolute lack of clouds in the sky, we're probably going to have a really boring sunset here in the St. Louis area. But the reason that I put this show in the list is I'm pretty sure we've talked about why the sky is blue, but we've never talked about why the sunset specifically isn't always the same red. And there's a new website that I stumbled across called Sunset WX, and it allows you to predict whether or not, and you have to pay for it, I do admit to that, it will predict whether or not you're going to get a truly awesome sunset. And the science behind it's kind of cool. And I'm like, this is science that is true everywhere. And we should talk about this because one of my favorite images, the one that I use as the background, is a sunset on Mars, which is this fabulous shade of liquid blue, which is actually the color I painted my home office. And all of this is because science.
Because science. Okay. So, and where do you want to start here? So should we talk about sort of like when you're seeing a sunset, what are you seeing? And I guess we need to sort of like, what are you normally seeing when you're just like seeing the sun in the sky? What are we actually seeing?
So if we were able to like get rid of our atmosphere,
please don't.
Yeah, no, we're not going to do this.
All right.
But if we could.
All right. But we're not going to.
No.
Okay.
If we could get rid of our atmosphere, we would have like a stark shadow exactly where day turns to night, and the sun would just sort of go, zut, hi, I'm over the sun, I'm over the horizon, you get no more of me, and now you're plunged into darkness. And during daylight, when we looked up at the sun, we'd see this white star hanging out, blinding us, irradiating us, because there's no atmosphere to protect us. We'd die, but we'd die while looking at a white star.
Right, because as we all know, that is the color of the sun.
Yes.
Yeah, it is white, not yellow. And that's what you see when you're on the moon, right? When you're up on the moon, and then you just see all of those photons, they reach your eyeballs with nothing in between, and you just get the raw, pure sunshine effect.
Which is why the Apollo astronauts had visors that were coated in, among other things, gold to reflect away a great deal of the sun's light. And now we don't have blind astronauts, and I'm also in favor of that.
Okay, so that's, were there nothing, that's what we would see. But now we've got some atmosphere, which you destroyed, but now we can bring back for the next step of this. So what are we seeing when we're seeing the sun through the atmosphere?
So during the day, sun high up in the sky. When we look at the sun, we see this yellowy orange ball. The exact color depends on how much water vapor is in the atmosphere, where we are on the surface of the planet. But when the sun's high in the sky, the reason it's yellowy orange is because a lot of that blue light that's coming out of the rainbow distribution of the sun's black body spectrum, a lot of that blue light is getting scattered by the molecules and atoms in our atmosphere. And as it scatters around, again, this is the blue light, some of it gets scattered down towards the surface of the planet, and that's what we see giving the sky its blue color. All that is bounced around, scattered light that bounces enough times that it bounces back to our eyeballs.
And we have, of course, done a whole show on this. Why is the sky blue? So it's like the blue spectrum of the rainbow, of the light, all the blue photons are the ones that are getting scattered the most. And so they're the ones that we're seeing, while all the other colors generally go in a straight line to where they were intending to go, while the blue ones can kind of come at you from anywhere.
Yes.
Okay.
Yes.
All right. So we're looking right up into the sky. We're seeing the sun. We're seeing it through the atmosphere. We're seeing both the color of the sun changed because of the scattering of the atmosphere. And we're also seeing the blue light from all directions because the blue photons are getting scattered by the atmosphere. So now then what happens when the sun is low to the horizon and it changes in color?
So for those of you who are watching this live on the internet, I'm holding up and trying to get away from reflections, a CD case that has a blue CD in it. Now, the rest of you are just going to have to imagine this in your head. So imagine that you're looking at the face of a CD that's kind of blue. Now, if you're up at the top of the center part of the CD, the part that you put it in your CD thing and it makes it do the spinny thing, we're going to pretend that center of the CD is the planet Earth. Now, if you're at the top of that and you look straight up, you're looking through the narrowest possible amount of your atmosphere. So the amount of light that gets to you, it's a lot of it, and it hasn't had to travel very far, so it hasn't had as many chances to get scattered away. So in the distance from the top of the atmosphere to the top of the Earth, it scatters the blue sky. Now, when the sun is instead off to the side, when that light travels to you, it has to travel through a much larger distance as it goes all the way across the horizon, all the way out through the side of the atmosphere. And this much greater distance the light travels, well, that larger column is able to scatter a larger and larger percentage of the other colors in the sun's black body curve. So it's not just scattering the blue, it's now scattering the green. It's starting to scatter the oranges, the yellows, and even the reds. Now, the reds are the hardest to scatter. Now, this is why we see the sun for the most part as red, because all those other colors, they've been scattered all over the sky, and some of them get to reflect off of clouds and other things. But what's really cool is the amount of light that gets scattered. It doesn't just vary with the distance the light goes through the atmosphere. Otherwise, sunsets would be the same color all the time. It also varies with, well, how much moisture is in the atmosphere, because the moisture actually increases the amount that the light of the sun bends. It also depends on how much pollution is in the atmosphere, because that increases scattering as well. So if you're living near an oil refinery like I do, you get pretty sunsets, especially when it's humid. If you are living somewhere where a volcano has just finished doing its thing, all of that aerosolized stuff floating around in our atmosphere, it helps to scatter out more and more and more of the sun's light, getting you these deeper and more vibrant sunsets.
And so, like, if there were no clouds, if there was no, pollution in the atmosphere, all that kind of stuff, like say you're looking through 20 kilometers of thick atmosphere when you look up, but maybe you're looking at, doing the math, like 40 or more when you're looking off to the horizon. It's giving that, I'm not sure the exact numbers. So
yeah, Fraser is
don't write
up
that down.
Numbers.
I am making up numbers. But so then you're getting, more further down the spectrum is getting a chance to scatter away. But, and that's just like without any extra stuff. But when we have those aerosols in the atmosphere, like around where I live, we get forest fires a lot.
Yeah.
And that will cause just insane sunsets. It'll cause, like, sometimes if the forest fires are really thick, you'll get like the sun looks like it's having a sunset when it's directly overhead. It turns this red color, and you can just barely make out this red disk, even though the sun's directly overhead and the sky is clear. Other times, it's not directly around you, and you get these sunsets because it's the aerosols are sort of off in some direction. You're seeing through that, but why do we get those crazy colors when we have those clouds? Because I mean, the clouds and sunsets really go hand in hand.
And this is where the amount that the light gets bent, the refraction quality of the atmosphere also starts to matter. So you have two different things that are going on. One, you have the light that's trying to come straight towards you is failing because it's scattering all over Kingdom Come. And eventually it's going to get bounced off of a different part of the atmosphere. And if you're lucky, it makes it back to your eyeball or your camera lens and onto your film or CMOS chip. Now, some other parts of that light, they're trying to shoot off in some different direction. But as they pass through the atmosphere, and all of the light is bending at a different point. So even the light that we're calling coming straight at your eyeball, it really got bent by the atmosphere. But we're using that as the test case. The light that you perceive as having come straight from the sun.
But that's why, I mean, sorry to interrupt, but that's why, like, when the sun is close to the horizon, it looks all wibbly wobbly,
right, and
out of focus, because even though there may not be any clouds around it at all, but it's just the sun itself is having to go through so much atmosphere. The light is getting distorted and refracted around that it's not able to take that nice clean path to your eyeball.
Now, some of the light that was never going to make it straight to your eyeball, it's going up through the atmosphere, and it's getting bent various amounts depending on the moisture, the temperature that's in the air. And that refraction is what we call this bending. This refraction of the light is causing different colors of light, first of all, to bend at slightly different angles, which is cool. That's why we get rainbows.
Yeah.
And then these colors are hitting the clouds. And so you end up with different parts of the sky where different parts of this rainbow have refracted, and where there's different thicknesses, so you have different amounts of scattering. All of these different factors add up in really hard to calculate ways, which is why it's 2016 and we, for the first time, have a website that you can go to. And so now that we can go do this, we're starting to be able to do this. It's because we're being able to start making the real-time calculations of, at this altitude, it's this humidity, this temperature, these other factors that go into refracting the light and scattering the light. And it's the combination of these two things.
Right. So without, like, if there were no clouds and you just had the sun, then all of, as it's getting close to the horizon, it's still going through all this refraction, and I'm kind of imagining this light sort of exploding out of it, scattering off the sun in all these different directions and all these different colors, but there's nothing to catch it. And so it's all just sort of heading out into the air, and nobody sees it. But as soon as you get those clouds up, from your perspective, it's like you've now got a place for all that light to fall onto. And so then you're getting these different colors depending on, as you said, the thickness of the air, the moisture levels, local temperature gradations, aerosols in the air, etc.
And in figuring out exactly where to go to get the absolute best possible sunset, it looks for where are those high clouds. So you have two things that you're taking into consideration. How much is the light getting scattered and refracted so that we end up with the potential for dynamic colors? And then once we have the potential for that, where are there the right amount of clouds? Because if you end up with too many clouds, it's just kind of dull blanket of gray. If you end up with just the right clouds reflecting the light. And so what they look for is nice, thin, high altitude clouds. Because first of all, those are tied to moisture. Moisture, good. Second of all, beautiful scattering in your photos.
And ideally, volcano going off nearby.
That does help. I recommend that over pollution. And to be clear, so Skyfire is the app I was looking at. That costs you money. It's designed for photographers. But the one that's free is Sunset WX. And I sort of combined that into one name with a cost. So Sunset WX is completely free. And then the app that's designed for photographers is Skyfire.
That is really cool. I'm going to play with this all the time.
It's really cool. So they have maps that allow you to look and figure out where are the cool places. And then they're tracking their success using Twitter. So when people post things up on Twitter, they're like, okay, this city with this word sunset, do we have it right? Do we have it right? Yes, we have it right. And when they don't, they're modelers. They refine their software. This is what scientists do. And these guys are scientists.
It appears to only be for the United States and Canada and Mexico. So those of you in San Francisco at the time that I'm recording this are going to have a beautiful sunset, as well as the folks up around. It looks like Winnipeg.
So Sunset WX does the whole world.
Well, this is the one I'm looking at right now, the Sunset WX. Yeah, and it's only the States, but maybe they have more sections added. This is super cool though. Wow. And I guess you can like put in some kind of, maybe get some announcements. Anyway, all right. So I think we now understand sort of why we're seeing the great sunsets. How does other worlds play into this? I mean, we talked about Mars. They've got like a totally different sunset, right?
Right. So Mars has much less atmosphere. And with less atmosphere, you get less scattering. And the atmospheric composition, it kind of is a little dry, you might say. It has water vapor in the atmosphere, but for the most part, it's not what we would call humid by a long shot. And it's very cold. And so you have ice crystals, which are, again, a completely different effect. And so during the day, you have this beige, for lack of a better word, atmosphere. It's kind of boring, kind of white. This is what happens when you don't scatter enough light and your eyeballs are like, meh, I'll call it white. But as the sun gets closer and closer to the horizon, you're starting to get the blues scattered, and you end up with this beautiful gray blue. If you're watching this live, the color of my walls, you end up with this beautiful gray blue color that you then end up with this pinpoint of white, slightly yellowish sunlight. And I think it's just kind of magical to look at.
It's such a neat idea that the blue that we're so familiar with, because the sunlight is being scattered all the time because of our thick atmosphere, can only really get rolling when sunset is happening on Mars, which is such a neat effect.
The closest you can get to a Mars sunset on Earth is to go very high altitude in the middle of summer at the equator, or close to an equinox, actually at the equator at high altitude. So get as much water vapor below you as you can, get as little atmosphere above you as you can, get the sun as close to straight overhead, and that color that you get down closer to the horizon it's not right, but it's as close as you get.
Now, there's a really interesting phenomenon that can happen during sunrises and during sunsets. Have you ever seen it called like the green flash or the blue
I
flash?
haven't, and I have a friend, Robert Sparks. He's a scientist down at the National Optical Astronomy Observatory, former school teacher, marathon runner, neat guy, who can catch green flashes on a regular basis, taking pictures of Kitt Peak National Observatory from down in the city of Tucson. And look up his photos if you can; they're truly phenomenal.
So what's going on with the green flash and the blue flash?
It's at a very precise atmospheric condition. As the sun is below the horizon, the green light gets bent over the horizon from the sun. So it's getting refracted through the atmosphere just right, so that if you're at the surface of the planet, you'll see for an instant this flash of green.
That is really cool. And then it's even trickier to get the one that's blue because it's further down the spectrum. I've even heard that people can see like a purple flash, but
they're lying.
Oh, really?
I mean, I'm just calling. No, they may not be, but it
right.
Just that's
extreme.
Sort of like, yeah, it's like winning the optical lottery.
But say you want to get a shot at it, right? You need to be looking. You need a nice clear view right to the horizon, ideally, at the ocean. And unfortunately, like where I live, I've got mountains to the left of me and mountains to the right of me. So like I've got mountains in the east and mountains in the west.
And the thing that amazes me, because I didn't know you could do it, but I've seen the photos, is Robert's actually able to get pictures of the green flash with the light coming up over Kitt Peak. And so it's not actually a flat horizon. He's getting it as the sun goes below the mountain range.
Oh, but it's still low enough and still off an angle. Well, then maybe it's all hope isn't lost.
I think it's worth trying.
I will give it a shot. Although it's always cloudy, so we never see the sun anyway. We're not even sure it exists here. But so one other, I think, kind of related is when we see the moon turn that beautiful red color during a lunar eclipse.
Yes.
Sort of a really similar. Yeah, what's going on with that, and how's that kind of related? How's because it's sort of the same effect, right?
It's the exact same principle. So in this case, you have the sun's light getting refracted around the planet, and as it goes from the daylight side of the Earth through the atmosphere over to the eclipsed moon, the more stuff we have in our atmosphere, the more colors are removed. So if you have a really nice clean atmosphere, you end up with a gray moon during eclipse. Doesn't make for great photos. But if a volcano's recently gone off, if there's a lot of forest fires, those different things can add up to enough stuff in the atmosphere scattering the light out that you end up with this beautiful blood red moon. And what's kind of cool is you'll see different parts of the moon are slightly different colors based on different compositions in different parts of the atmosphere, and the sunlight's refracting through in different places.
It's interesting. I know, like every time that a lunar eclipse is coming, we'll be able to tell people based on sort of where it's going to be moving through the atmosphere. The scientists will report on whether it's going to be a nice blood red one or whether it's going to be a lot more muted.
And we're not always right.
No, it's like making predictions about meteor showers, but it's really it's an atmospheric effect. It's like the atmospheric modelers are the ones who are providing the data to say it should be a good one, or it's gonna be pretty weak. Although it's always great. It's always worth seeing. There's one other world that we got a chance to see, and we got a chance to see its sunset, which was Pluto.
That's true, and that was something we weren't really expecting. Now, we didn't see it from the surface, but from looking at the sun passing all the way through the atmosphere to the spacecraft that's experiencing sunset the same way astronauts in the ISS experience sunset, sort of. They saw the tholene-rich atmosphere of Pluto scattered enough light that you ended up with this gray-blue sunset.
Yeah. It's a beautiful picture. Yeah, this amazing picture of Pluto itself, and now the disk is completely obscured because the sun is behind it. But you get this amazing atmosphere around it, and it really is this crazy blue, circle that goes around the actual disk of the planet, and you
Yes.
see. So if you were standing on the surface of Pluto and the sun was just at the edge of the horizon, you would probably get something similar to what you see on Mars, right?
Yeah. It's not quite as rich of a blue, but it's very similar.
So if we could travel to other worlds around the universe and sample every possible atmosphere that was out there, what would make for the greatest sunsets and sunrises that you could sort of humanly imagine?
I think so. You know how different liquids, like Italian salad dressing, you end up with different densities floating on top of one another? Well, you can imagine different atmospheric events that cause a highly stratified atmosphere. And with a highly stratified atmosphere, you actually have the chance for a stripy sunset. And I think that's just a really cool idea.
Oh, that would be cool. I mean, you could have like different cloud layers and then different different thicknesses and densities of the atmosphere in each one. And oh, that would be amazing.
Yes.
Yeah.
I'm a fan of stripy things.
Does that happen naturally here?
So we don't have a highly stratified atmosphere in terms of like very distinct layers. But one of the things that's cool in some of the Pluto photos is there appear to be standing waves in the atmosphere of Pluto, and we don't know why. Don't know why.
Yeah.
And these are gravity waves as opposed to gravitational waves, which LIGO detected. And these standing waves have these discrete density stripy bits, and you can see them through the atmosphere in the pictures. And so, yeah, this happens. We've seen it.
Oh, that's amazing. Cool. Well, I think now we should all head out and look for the next great sunset.
It's true. So,
right.
So that free site is Sunset WX. They've given us no money. I just think it's cool.
Yep. And there's an app.
Yes.
I want the app. Okay.
The app is the other guys. The app is Skyfire, not free.
That sounds great still. All right. Thanks, Pamela.
Thank you.
Stop.
And we save, and we bore our entire audience for a moment.
Oh, this is their favorite part.
This is 411.
411, yeah.
Oh, man. We should have done something tied to the number, but I guess that's strictly a US thing.
411?
Is information.
Okay. Yeah, it's the same here. But who does that now? You have the internet.
People who like to talk to other humans and are weird.
So I was wrong. It's sunrise. Sorry. So if you live in the San Francisco on the north coast of California tomorrow, you should get a really nice sunset. Sunrise. Sorry, it's sunrise. Or if you live in, man, I don't know my states.
If it's sunset in the morning, we are in such deep trouble.
Yeah,
okay, so are you on Sunset WX?
Yeah, and then is there like an
where
option?
Are you looking?
So
no, but I know my states fairly well.
Oh, okay. Hold on. We got no. All right. So for sunrise, you're sort of like the 2 above Florida, 3 above Florida.
That's one of the Virginias.
Yeah. The one with the sort of the one below New Jersey. Yeah.
So that's Maryland.
Okay. Yeah.
Flat on the bottom or flat on the top?
Flat on the top.
Flat on the top is Virginia.
There you go, Virginia. If you live in Virginia tomorrow, right on the coast, you should get really nice sunrise. And then tomorrow for sunset, right here, apparently, is going to be nice.
That is cool.
Yeah. Western Oregon, Virginia again, and like Montreal-ish should be nice. And then right in the middle, like kind of Colorado-y area. So there you go. This is really cool. And they actually do have, I slandered them. They do have global forecasts. So you've got sunrise in the world. So let's see what our Australian friends are going to have. Not great sunrise. And then sunset world. Not a great sunset unless you live right in the middle. But Western Africa is going to have a really beautiful sunset. So there you go. This is really cool. I'm really excited. Yes. I love this. I'm going to use...
This is why I wanted to do this show, because I saw this and I was like, this is like going to suck my life. I'm going to turn it into an episode.
What wonderful people made this. Huh. Okay. Let's see if we got some questions. Susie, pretending to be Astronomy Cast, says, I saw the green flash in February in the Florida Keys, the only time ever. Fantastic. And that's the green flash. So now you got to see the blue flash. Peter Liverdink says, as a red-green colorblind person, I think the green flash is a myth. You should be able to see only the green flash. Nancy Graziano says that I am the astronomical version of Steelers wheel stuck in the middle with you. Yeah, exactly. I am stuck in the middle of mountains. But you go to the west coast of Vancouver Island, and then you just got, it's good. Nancy is also saying that Alan Stern or Alice Bowman showed New Horizons photos of the stratification of Pluto's atmosphere at Neef and said it was absolutely gorgeous. So
cool.
Kyle Carmichael saying, now Fraser, you're making Canadians look as bad as geography. Still not as bad as us Merkins, though. My wife is American. And
my husband's Canadian, but it's not the two of us.
Yeah, no, I know. And and I think I've traveled to more states in the United States than she has. So I know my American, but that coast, it's a lot of little places all mashed together, and I don't really understand it. Once you get on the towards the west, I've got it. Canada represent. Okay, let's see. Macaroni is saying that sunset is on right now at the ISS live feed. Well, I guess that was like 5 minutes ago, and they're halfway around the world again. So Nancy Graziano is asking, since the level of man-made particles and pollution is greater today, is it safe to say that our sunsets today are more vibrant than they were in the pre-industrial revolution or 5,000 years ago or more? Didn't they used to get really nice sunsets and sunrises in LA when their air pollution was so bad?
Yes. And pre-industrial revolution, they probably had much worse sunsets, except when like Krakatoa went off and stuff. But then things are getting better, because if you think back to when everyone was burning coal for absolutely everything, the streets were literally black with soot. And so we're getting better again, which is a good thing and a bad thing.
Yeah, it's good for our overall health, respiratory diseases, and but bad for sunsets. Wah, wah.
It's true.
Yeah. Anything else? Nikolai Petrovsky asks about sunsets and sunrises on Saturn.
It doesn't have a surface.
Well, pretend you could float in the atmosphere of Saturn and look up at the sun.
Well, once you hit a certain depth, it would just sort of be like red, and then it would just be dark, and because it's all scattering. But when you're near the surface, as you go through the layers, you'd watch all the colors starting with the blue going down to the red scatter out.
Right. So you're always going to get that same
set of rules.
Yeah, it's going to start blue, and then it's going to, and then it's going to move from there. Okay, cool. Well, I think because we are doing this at a funny time, we don't have a lot of questions today, which, did you watch the SpaceX landing? Have you seen the SpaceX landing?
Yes, when they stuck the landing.
Yeah.
So I was actually a really bad human. I was in the Astronomical Society of the Pacific's board meeting, and Susie, you're awesome. I think it was Susie mentioned to me that we were a few minutes away from landing. And if it wasn't Susie, it was a friend I bike ride with named Bert. I'm trying to give credit to whoever was the person who helped. Someone told me they're getting ready to land. So I switched on Twitter, found the live feed, and I'm secretary of the board. So I'm like taking notes and watching the feed, taking notes and watching the feed. And then they stuck the landing. And as soon as the next person was like finished with their sentence, I like reduced myself to that interrupting middle schooler, you know, the one who's like, ooh, I saw this thing on TV. Yeah, that was me. So I interrupted the entire board meeting to make sure everyone knew SpaceX had stuck the landing. And they sort of stared at me like you stare at that over-enthusiastic 12-year-old in science class. And then they went back on with the rest of the meeting.
It's only just like one of the most important things that's ever happened in the history of spaceflight.
Cool.
Oh, yeah.
But
yeah.
So did you notice when it landed, it like skittered a little bit sideways?
Yeah.
And it's on a boat that's like in water that has like waves. And so my whole brain is like, don't get hit by a wave. Do not get hit by a wave. Because I'm like, don't fall over.
Yeah. So we talked about this in the Space Hangout today. There was 50-mile-per-hour winds. And so if you see it came in at an angle to compensate for those 50-mile-per-hour winds. And then the other part is that they don't have a lot of ability to really sort of throttle the engines down very far. So it has to come in fast.
Yeah.
So it comes in fast at full thrust and then just happens to land. And it's like the perfect timing. It's just what an unbelievable accomplishment, you know?
Yeah.
All hail Elon Musk.
I'm going to be so glad when they're landing on hard ground.
Yeah. Now they've done the hard part. Now they can go and do the easy part, which is land on hard ground again. And then,
but I suppose there's still going to be some orbits that they're sending things to where they're too far from land and they just can't get back to it.
Yeah, the rocket's just too far downrange, and
right.
They've already figured out the hard part. So now they can catch those ones that are going downrange, and they can catch the ones that are doing a more reasonable orbit, or the amount of fuel that they have enough fuel left in the tank they can get back to the launch pad. Just a stunning accomplishment. What do you think now? Have you been following the sort of plans from to send a probe to Alpha Centauri? Did you see that?
I saw that, and part of my brain is going, huh? So where I get stuck, and I need to read more on this, is they're sending this wee thing.
Yeah.
And how do we get any signal back from it? It's not big enough. Are we simply sending a message?
That is in the question mark part. So how we get a signal back from these things is still an unsolved problem.
Okay.
Yeah. And
I was good until I saw the size of it.
And if you look at the time frame, it's like 50 years is when they think they'll actually be able to start like sending these missions. But they're spending, they're starting to spend. I mean, the important part is that Yuri Milner, super rich guy, and has already funded a ton of SETI research, is going to be throwing piles of money at this to get the engineering going. And I think the other part that's really important, right, is like, we all get excited like, oh, it'd be so great to send a probe to Alpha Centauri. Well, wouldn't it be great to just send a probe to Mars that could get there in, I don't know, a day?
A couple months,
right? No, like a day.
Well, so the acceleration problem, they still have to accelerate, and it takes a long distance to accelerate over.
Well, I don't know. Yeah, I'm not sure how long it takes to do the acceleration, and then whether you could have other ones on Mars that would do the braking. But you can kind of imagine, if this technology gets figured out, you can imagine these probes getting just shot really fast from world to world using these laser systems. So I think, the big picture one of like, yeah, let's send a probe to Alpha Centauri that we can never talk about. And it's going to be moving at 20% the speed of light. And it's just going to get ground up by the interstellar medium to dust. Maybe, we don't know, is one problem. And that's why, they're like, we're going to send thousands, which is great. By all means, send thousands. If they can figure out the way to get them to communicate back. But I love this idea for in our solar system.
I think Kim Stanley Robinson's new book, Aurora, which may actually not be a new book. His book, Aurora, I think actually talks about the concept of using lasers to speed things up and slow them down for interstellar travel.
Yeah. What about having balloons, right? Blimps up way up in the, at the very limits of what's possible, and then they could have lasers on them, and then they could release probes and zip, 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 zap them up into orbital speed. Like, I think this is a really exciting technology because your propulsion system is not stored on your spacecraft, and you're giving things, the highest possible impulse that you can have. I mean, there's nothing out there that moves faster than light. So
it's still, so the thing you have to remember, this is a lot like an ion drive. So you're going to have ion drive like kinds of accelerations, which is what we see with the Dawn spacecraft, where it's like, I think it left orbit. We're not entirely sure. It moves
Give it a week.
slowly. Yeah. And so when we accelerate things with lasers, it's pretty much the same idea, except instead of accelerating particles, which have a fair amount of mass to near the speed of light, we're taking actual bits of light and using their momentum bounced off of something. It's still accelerating by throwing BBs at something. So we're going to very slow acceleration. But as it accelerates and accelerates and accelerates, you can achieve very high speeds. So part of why it has to be so tiny is because light is ineffectual. So every bit of mass that you have, it's hard to accelerate that. So by making it tiny, the conservation of momentum allows it to overcome faster.
Yeah. And, if you go back and listen to our show about solar sails, we talk quite a lot about how it's not about like taking your solar sail and aiming at the target and, going directly there. It's about orbits, about raising and lowering your orbits. And so you can imagine a situation where we could have, you could have like laser arrays in orbit ahead of Mars, behind the Earth, right? And then, so then you launch one of these little spacecraft, the one that's behind the Earth or at the Earth, points at it, starts zapping it, raises its orbit up so that it's on more of a trajectory that's going to interact with Mars. And then the one at Mars is there. And then as it's getting closer and closer, that one starts to zap it again and lowers its orbit and decelerates it. And then you've transferred stuff from one planet to the other quickly. You can, the more power they can do, the more they can make more of a direct route. It's it's a whole wonderful direction that has so much promise that I think it's just so great that they're doing it. And it feels a little, I don't know whether they did it to say like, here's the big plan is that we're going to send probes to Alpha Centauri in only 20 years, when there's so much use for that kind of technology just here in the solar system. That it just
it's the time it takes to accelerate things. It gets annoying for human beings who are trying to go shorter distances. So super effective for longer distances, super effective for longer missions that need to have that regular supply like Dawn.
Yeah.
But it's just not as good for a lot of other things.
Like that's one technology that we should really focus on. Another one would be great is rotating spacecraft.
Yes, right? Yes. That one, we need to get on that one right now. Babylon 5. I want that station. I don't want the shadow creatures.
Yeah.
But I want that station.
You don't want the shadow creature? Okay. or the one that was in The Martian, right? That, the Hermes with its big rotating regions, cool. Or what they did in 2001, right? So we don't know what what will it feel like? What will the centripetal force that you're going to feel as you're in one of these rotating things? Is it going to make you vomit, or is it going to be sustainable? Is it actually going to protect you from the problem of microgravity? Like the second you go to space, you're living on borrowed time. So, if you don't have some kind of gravity, and like one of the things that I haven't even been like, we don't know if humans can survive on the moon. in the low
long
gravity,
term, the radiation
the
issues
15.
and the
Well,
gravity issues. Yeah.
even the radiation, like even you solve the radiation issue, can we be healthy in 15% of Earth's gravity?
Right.
We don't know, right? We know that
Right.
we can't
That's
be
totally
healthy
true.
in microgravity, but we don't know if we can survive in 15%. And we don't know even if we can live on Mars, right? It's 30%.
Yeah.
Can we, will a human being survive over decades in 30% Earth gravity? We don't know.
And the standard question is, if you have children, will they ever be able to come home? And the answer is probably not.
Probably not. Yeah. In The Expanse, they cover that it's like the Earthlings have this advantage because they can go to all the other worlds, but the people born in on Mars, on Eros and stuff, they can't survive anywhere else. So I think it could very well be that the only way that we can survive, the only planet that we could live on in the entire solar system is Venus. And obviously Venus, is worthless. So, and otherwise it's going to have to be orbital facilities. It's going to have to be rotating. Pamela's classic: take an asteroid, drill out the middle, set her spinning. You got yourself an O'Neill cylinder. Yeah, we'll call that the Pamela special. And that's the only place that we can live. We can't live on Mars. We can't live on the moon. We don't know. Yeah, can't live on asteroids. So, anything else interesting that happened? Oh, did you see that? No one's asking any questions. Are they just like slack-jawed listening to us?
There's 27 of them out there.
I know. And are they just slack-jawed listening to us?
They're cheering on the B5 reference.
Yeah, about space exploration. Did you see that the Blue Origins did the third test of their rocket?
No, I didn't.
Yeah.
So, I did note that there was 3 different commercial things docked to the ISS at the same time. There's the Bigelow, the SpaceX, and I missed what the third was. I just knew there was a third.
Well, the Bigelow one is so cool, right?
Yeah, because but they're not allowing the astronauts in it.
Ever?
At least while it's in test phase.
Yeah, well, that makes sense. I mean, it's like the astronauts get their bouncy castle, but they don't get to use it. It's so sad. But I mean, can you imagine being cooped up in these tiny little tubes, and then you get one of these, whatever the production version of this is going to be, and it's going to be this gigantic open space that they can float across and bounce off the walls and live in and not feel so cramped. I think once they get that figured out, it's going to be wonderful.
So I am going to point out something that's making me stupidly happy. When we started this episode, it was really bright daylight outside. It isn't now. And I have new programmable light bulbs, and the light bulbs in my room turned on the lights without me having to do anything, and they did them in a slow, gradual way, so it didn't totally screw up the lighting in this episode.
That is so cool.
Light bulbs.
What were the light bulbs that you used?
It's the Philips Hue white ones. They aren't even the color ones. It's the lame ones. I got them to try, and they just totally rocked my world. How
did you make them change brightness based on time or the brightness of their sensor?
So I don't have it that sophisticated. I have it set to slowly turn on over about an hour so that they're fully bright at the time that is current sunset.
Oh, we are living in the future with rockets that land themselves and inflatable habitats and light-powered interstellar probes and lights that get a little brighter when it gets a little darker. This is truly the future. I don't even need a flying car now.
This is the first time we've done an episode at sunset, and my lights haven't been totally screwed up.
And you can test it out. That's awesome. Yeah. Cool. All right. Well, let's wrap things up for today. Thanks everyone for watching. Pamela, thanks for bringing the brain. And we will not see you next week, but we will see you the week after that.
It's true.
Awesome.
Okay.
All right.
Have a great time.
Thanks everyone for watching. See you all in a week and a half.